So today I would like to talk to you about some things that we learned when we started to work on join ordering in Apache Calcite. So before I start, a few things about myself. So currently I work at Queryfy Labs, where we work quite a lot with different query compiler, query optimizers and data management systems. And before that, I worked at GridGain, where I worked on Apache Ignite. So and now, let's go to the problem itself. So it's, I think it's quite well known that join ordering is one of the most important optimizations during the query optimization, and the reason for that is the fact that if you switch the join order, you can get plans that differ in execution time and the execution cost by the orders of magnitude. And the problem is NP hard, so different heuristics do not work in a sense that they not guarantee globally optimal plans. And obviously Apache Calcite has some built-in rules, some built-in mechanics to optimize the order of joins. However, what we see in our practice is that it has some issues that are repeated across all the projects. So basically, this presentation will be a short compilation of things that we learned over some time, and essentially I can separate two things that consistently came across our minds. The first one is that well, the default rule set for working with joins in Apache Calcite consists of join commute rule and push through left and right rules. So the first thing that we saw is that the default rule set does not do the exhaustive search, and even when we started looking into that, we saw that there was already filed an issue that was where it was explained how sort of overcome this thing. And another consistently repeatable issue that we see is that the more tables you have, the larger planning time is. And this is a fundamental restriction, but the boundary at which the planning time exceeds some reasonable amount is reasonably low. And usually it's somewhere around 6 tables. And in practice, this limit is quite small for a practical approach. And usually what projects do is they fall back to some heuristic rules that try to optimize the join order somehow, but do not guarantee optimality. The question that we would like to ask and give some potential directions and discuss with the community is what we can improve in Apache Calcite in order to probably raise that limit to be more practical. And so for the sake of this presentation, we will do some simplifying assumptions, which can be obviously be overcome in practice, but they will also complicate the presentations. So we will consider only one join implementation. So let's say it would be hash join, so no interesting orders, for example, for merge joins. We assume no hypergraphs, so no conditions that touch 3 or more tables. And also consider only inner joins. As I said, there are known techniques that allow to overcome this, but it just significantly simplifies the talk. Now, why the complexity? Why this is a big deal? The thing is, the more tables you have, the more fundamentally, the number of possible joint orders and joint shapes you can have. And this number basically is produced by two factors. The first factor is the factorial from the number of joint relations, and you can see that by basically dissecting the possible joint orders into order of leaf nodes, like we have in the picture, and the possible tree shapes. So the possible of joint orders of tree nodes is the factorial of the input relations, and the number of joint tree shapes is the Catalan number of the n-1. And it's clear that since it's a factorial of n, it's a product of n factorial and Catalan number, the number of possible joint orders grows faster than exponent. So even for 8 tables, it already exceeds exceeds millions. And in practice, we want somehow to limit the number of possible options that we want to consider. And one of such assumptions that allows to limit the search space is cross-product suppression. So essentially what we say is that we do not consider plants where a cross-product exists. Of course, this is a heuristic. This is also a heuristic, but in practice, it is considered a quite good heuristic. So, of course, strictly speaking, there are plants with cross products that can be more optimal than the ones that without cross products. But since the very early academic work on joint ordering, this is a heuristic that is considered to be useful. And it turns out that when we remove plants with cross products and leave only plants without cross products, the number of possible plants, so essentially the search space, is reduced significantly. And for example, for TPCDS query 17, if we consider only cross products free plants, the number of the search space cardinality becomes almost 100 times smaller. And now, when we talk about cross-product free plants and joint ordering in general, now let me also introduce some theory that we will use later. So one thing that we want to consider is the joint topology graph. Essentially, the vertices of the graph are joint relations, and an edge in a graph is a joint condition. And for analysis, it's useful to consider some certain shapes of the graph, such as clique, star, and chain. And the good thing about these topologies is that for them, we can precisely estimate the number of possible joint orders. And also we can precisely estimate the number of groups in Apache Calcite memo, which we will also use for some practical results. And now that we have a joint topology, so we have a set of relations that are being joined and the conditions, one of the things that many optimizers do is join order enumerations. And since we only consider cross-product free plants, we are interested in algorithms that take into account this graph and produce only those plants that contain no cross products. So of course we can enumerate all possible orders and test if a plant contains cross product, but that would be quite inefficient. So one of such algorithms that turns out very good to be used in let's say very good to be used in combination with Apache Calcite is graph-aware top-down enumeration. So it's essentially the idea of this algorithm is that we have a essentially the duplication structure, which is quite similar to memo or dynamic programming table. And we start splitting our topology graph into partitions. So let's say we split it into 4 and 3. And then we recursively descend into each of the parts of the graph and memorize the decisions that we already explored in the dynamic table. So we further split, for example, this graph into 3 and 1, and since there is only one order for one table, so we immediately memorize the R5 into dynamic programming table or the memo. So then we descend further. We consider this clique of 3 tables, and then we enumerate all possible combinations here. So we descended into 2 tables. For 2 tables, we only have commute, so we can join A to B or B to A, or R1 and R4, R and 4 and R1 here. And once we have optimal plan for a pair, we return back in the recursion tree and consider other combinations that are left in this graph partition. So once we explore all the combinations, for example, in this clique of 3 tables, we already have an optimal subplan for these concrete 3 relations. And then repeating this procedure again and again, we finally end up with an optimal plan for this particular join graph. And the the memo dynamic table is used to avoid executing duplicated work. Now, how can we do this in Apache Calcite? Essentially, in Apache Calcite, there is, let's say, an infrastructure that would allow us to implement such an algorithm. And this infrastructure is called multi-join. So it's a set of rules that runs in a heuristic planner, and essentially it executes in 3 steps. The first steps attempts to combine all adjacent joins into one relation that is called multi-join. So essentially we combine all neighbors into one node, and this node contains the information about the relations, the conditions. So essentially in this multi-join, we have the topology graph. Then we can execute arbitrary algorithm that orders this relation. And finally, this rule then produces an alternative join tree that can be further used in subsequent optimizations. One thing to note is that currently there are a few rules that employ multi-joins, and one of the interesting rules is a lopt optimize join rule, which essentially a greedy heuristic that produces an alternative plans that are further used by Calcite in order to choose the best plan among them. One thing to note here is the multi-join is a logical operator, and but at the same time it produces n alternatives, and it is important that if you use this rule, it is important that the cost of logical operators that you use be aligned with the physical cost that you use in subsequent optimizations. Because otherwise, even though it produces the n alternatives, one of the alternatives will be chosen absolutely arbitrarily. Now, we have this multi-join concept, but how well can it be used with other optimizations in transformations that we have in Apache Calcite? In particular, how does it cooperate with transformations such as aggregate push-through? Well, it turns out that it's not very practical in a sense that we cannot consider multiple alternatives when we use multi-joins. We could potentially run this multi-join for every existing adjacent subtree of joins in MEMA, but then it would mean that we would need to repeat the multi-join optimization multiple times, which is not efficient. Usually this multi-joins, as I said, is used in heuristic, in a separate heuristic phase. Now, without multi-joins, how Calcite does the ordering? So if we put the multi-join aside, we have different transformations that are available according to join properties. We will cover a few of them because, as we will see, it is sufficient to enumerate the whole search space. So one transformation that is available fundamentally and as a rule in Apache Calcite is join commute rule, which employs join commutativity. And it says that essentially if we transpose the inputs of a join, we will get the same result. Similarly to commutativity, we have left associativity that does this transformation of a joint tree. Alternative, so since we are considering currently only inner join, similarly to left associativity, we have right associativity. And it can be shown that those transformations are already in a certain sense redundant, because, for example, I can show that, let's say, right associativity can be produced as a sequence of left associativity transformations and commute transformations. So, for example, if you have these three transformations plugged into your transformation-based optimizer, then already you will be producing some duplicates which are eventually deduplicated by MEMA. So from the theoretical standpoint, it is sufficient to have only commutativity or left to right associativity. Regardless of whether you're considering only cross-product free joins or cross-product or joins with cross products, you will still will be able to enumerate all possible alternatives. But at the same time, even if we leave out only commutativity and left or right associativity, so if we leave out only two rules, even in that case, you will be producing duplicates because, for example, in this picture, you can see that if I start with left top tree and then apply different rules, I will get to the same plan twice. And in practice, since rules are fired for each of the relations in MEMA, the number of duplicates also grows exponentially, which is not very good for for the performance. But another thing that actually makes things worse is the fact that Apache Calcite uses a relative addressing relative to the input rows. And when we apply, so let's say we have a complex join graph and we apply these transformation rules multiple times, we may end up in a situation when the same join, like here in the picture with A on the left side and B on the right side, can be produced with different formally different join condition. So semantically, this condition is the same because equality is commutative. But from the digest perspective, these two joins are different and they will not be deduplicated in memo. And if you have, for example, a larger number of join conditions, so you have, for example, 3 equalities, in a join condition, then the number of possible duplicates also grows exponentially here. Another issue that we, like I mentioned, that we stumbled upon in many of the projects is also a consequence of this relative input addressing. And the thing behind this is actually when you execute a commute rule, you need to produce the exactly precisely same row type as the original row. And since we flip the inputs, the actual row type of the join will also be reordered. And in order to compensate this reordering, commute rule produces a project node on top of the join node. And now, since we have this project node on top of a join, for example, in this picture, the associate rule would not execute, and the essentially the right plan will not be cannot be actually reached. So on having only commutativity and left to right associativity does not explore the full search space. By the way, by default, Apache Calcite has commutativity and left-right push through join rules. But again, those rules are just a combination of commutativity and associativity, essentially. And even with default rule set, the same problem is also relevant. In order to compensate for this shortcoming, Apache Calcite has join project transpose rule, which moves project on top of the join that is above the project. And after we do this transformation, we are able to execute associate or push through rule on the new join, but the shortcoming that we have here is that now we have even more semantically equivalent plans that are not deduplicated by memo. And for each such new join, more rules, the same rules will be executed again and again. So on top of the theoretical, let's say, explosion of the duplicates, we have these two facts that also contribute to the slowdown. And another thing that we noticed, but it was fairly easy to fix, is that by default, commute rule does not fire. It has an option to not fire on cross products, but the associate rules would execute and produce the plans with cross products. So we introduced an option to avoid that, and this improvement is available in the Apache Calcite version 1.27. So now, how can we improve this, and how big the improvement could be? Obviously, the last two issues could be addressed by using an absolute addressing of inputs for relational operators. And actually, this is used by some of the projects. For example, CockroachDB and Apache Spark use that. But in practice, this change is very large because essentially it will touch all all and every rule in Apache Calcite, and it will also touch the core logic. So at least at the moment, this change is out of our reach. But on the other hand, what we can do is try to use some probably, let's say, hacks or changes that will allow us at least to estimate the potential improvement that we'll have. So one thing that we explored is how to avoid producing that project on top of the join when we execute commute rule. And what you can do here without actually changing the sources of Apache Calcite is to introduce a custom join operator that has some internal state that would enforce the same row type when you flip your inputs. Obviously, since we're introducing a new logical operator, existing rules would not work with such join. But it's efficient for to run some estimates. And another downside of this approach is that prior to producing this custom join, you need to do some pre-processing and essentially collect information about the join graph that we were talking about. So in other words, using this custom join requires you to have a knowledge about relations that are not immediate inputs of this particular join. Another thing that personally I think can be fairly easily integrated even in the project itself is to try to do some expressions normalizations to avoid duplicates due to reordering of the inputs. And what we can employ here is basically to sort the inputs of well-known and widely used conditions. So for equality, you can immediately use commutativity. For inequalities, you often can flip the operators and change the operator itself. And if you have multiple join conditions in a relational node, then you can also sort those conditions, for example, by first input, then second input. So essentially do some lexicographical ordering. And of course, having widely and strictly normalized condition is a quite tough task because, for example, if we have this complex equality with nested calls, the task becomes trickier, but I think at least a best effort normalization can be used. And the way we try to simulate that is to essentially plug this normalization into custom transformation rules, because now that we have custom join nodes, you also should have custom commute and associate rules. So yeah, plugging these normalizations into rules themselves is not a universal solution. But now let me share some numbers that we observed in practice. So if we only remove the projects that are produced on top of joins and also do condition normalization, then the number of groups and the number of rule calls is reduced dramatically. So it's almost 200 fewer groups in the memo that are produced for some sample topologies, and also the number of rule calls reduced. And interesting thing here is essentially due to those duplications, the number of groups in the memo in without those optimizations exceeded the theoretical numbers that you can calculate for those star, click, and chain topologies. But once we have this optimization in place, the number of groups in MEMA is aligned with those numbers. And now, if we have those two issues solved, one fundamental thing that is still present is the duplicates that are produced by the compute and associate rules. And actually, in academia, there is a suggestion of how you can overcome that in transformation-based optimizers. And key idea here is basically there are two key ideas here. First thing is that we introduced a special, let's say, data structure that is associated with each join node in our optimizer. And this data structure essentially holds the topology graph information and the, let's say, flag about whether we already explored this particular graph or not. And the second piece of this idea is to use that topology-aware top-down join enumeration algorithm when we execute this rule. So essentially what we do is we replace those generic commute and associate rules with some custom rule that does this graph-aware exploration. And important thing here is that if we exploit this idea, then we are able to combine this particular enumeration rule with other transformations. For example, if we have an aggregate push down, then we just produce an additional data structure that encodes an alternative essentially that encodes an alternative graph. But at the same time, it is a common expectation that the number of, let's say, alternative graphs still will be fairly small. So that's why this solution is expected to work well in practice. And essentially what happens is when you execute a rule on a join relation, you do this top-down enumeration and produce a several number of, well, essentially you produce all alternative joins without running any duplications. And what happens is that the number of rule invocation becomes equal to the number of joins that will be produced. So fundamentally, there are no duplicates that rule produces. And for from the practical perspective, now that we have aligned the number of rule calls with the number of produced joins, essentially the speed up in rule execution is essentially aligned with the speed up that we have with the reduction of number of groups. So which is quite huge, essentially for simple topologies. And another practical consideration that I think is even more important than the number of groups and the number of rule invocations is shift in that boundary that we talked about in the beginning. So if we do just the first two optimization and we consider some time budget for the optimization, so having implemented first two optimizations will increase the number of possibly planned joins 4x. And if we do implement this top-down enumeration, the number of join relations that you can optimize is increased 7x, which actually can push the practical, push the cost-based and not heuristic exploration to quite a large number of practical joins. But of course, those things are, let's say, hacky, and what we are looking forward to is to discuss with the community what steps we can take here in short and long term, and whether the community feels that those issues are important for the projects being used in practice. So what we envision here is that in long term, we can try to evaluate and estimate switching to let's say absolute addressing. I know that it was already discussed on the dev list, and yeah, currently we think that this is probably an unreachable target, but probably there are some things that we did not yet consider, which will make this change more tangible. And another long-term solution that we can have here is to integrate this join set infrastructure into the core optimizer, which will allow us to implement this top-down enumeration inside out of the box with Apache Calcite. In a short-term solution, I think what we can have here is, first of all, since we have this infrastructure of multi-joins, we can implement arbitrary join enumeration algorithm besides the greedy heuristic, and the projects that are already using that heuristic can immediately use this new enumeration rule. And another thing to tackle, I think, maybe to integrate the expression normalization in the planner. And I think it can be, well, possibly, at least it's a discussion point, we can integrate this as a hook, and we can normalize expressions for each relational node that is produced by a rule. So, and potentially not only joins and join reordering is affected, but probably many other transformation suffer from these reorderings. And yeah, I think this is all what I wanted to share with you today. And yeah, giving the mic back to Stamatis.
Hey, Alex, thanks a lot. It was, at least for me, and I'm sure for everybody else, it was a very interesting talk and very, very well organized. So it really flows from one thing to the other. And I get some, I get some things to suggest, like the paper about the volcano transformation that you mentioned, that in academia. And basically, you had everything figured out. So not much to suggest. But yeah, I want to leave some people some time for questions. So I see that there is already one in the chat. It says, can you make an example of multi-join? Can one be automatically obtained by optimizing a group of join? How does it work internally?
So essentially, a multi-join is a separate logical node that is built in Apache Calcite, and also you have a set of rules that try to coalesce adjacent joins into a multi-join, and then after you do this, you execute this greedy heuristic that rearranges the join. And actually, if I'm not mistaken, in Calcite there is also a separate method in programs that is called heuristic join order that actually transforms your rules and replaces the built-in exhaustive, let's say, rules with this heuristic rules. So it will work almost out of the box, but the only thing you need to adjust is the cost model for logical operators.
Yeah, and probably worth mentioning that there are various projects that are already using this.
Right, right, yeah, and I think, for example, Flink always uses this heuristic ordering, so it does not even use the commute and associate and push through rules at all.
Yeah, and Hive as well. So for people interested to see how the multi-join works, they can look into various other projects where it's already incorporated. So yeah, Aman, you can ask the question yourself, I guess. Open the mic.
Hey, thanks for the excellent presentation, Alex. I was curious, the custom join operator, right? Did you integrate that with the LOPT optimize rule? And did it actually change, or did it preserve the original plan, or and the quality itself? And did you actually see any compilation reduction, time reduction?
Yeah, so we did not integrate custom join with lopt rule because it is not necessary, because actually lopt rule already runs fast enough, and it doesn't suffer from the from these points that we described. And what we had to integrate this custom join with were custom commute and associate rules, because built-in rule, because in those rules you need to encode this additional information about this project that you eliminate.
Thanks.
Any other questions for Alex?
I would like just to add that this problem that Alex highlighted is really important for the community, because in a downstream project we had a task to optimize joins, and like after 6 or 7 tables in one join, it's too slow to be practical. So like we had to do funny stuff on our side, and I hope like someday Calcite will be able to handle more joins. Thank you, Alex.
Yeah, I think that one point to mention is like Calcite can handle it, but you have to figure out how to put the rules together. And this is, yeah, the presentation by Alex is a very good point, because there are not many.
Yeah, but like the nature itself of join reordering like pushes optimizer to its limit very fast. So like either we should like reduce amount of rules and be ready to lose some other functionality in other areas, or like it's hard to get everything. So obviously it's about some compromises.
Yeah, I totally agree. And like I said, it would be very very good if we have these long-term solutions, but again, it's we need to understand whether the effort is actually worth the result. But hopefully, even some short-term solutions also can improve, well, can reduce the pain of existing projects.
I guess we can have another question for now, and then we can keep on the questions in the open discussion. So if somebody else wants to ask something right now.
I have a very quick question. I was wondering, Alex, if you have tried the join order benchmark with the kind of plans you produce, and what's the outcome in case?
No, we did not use any existing benchmarks, because well, the scope, like I said, it's a compilation of our experience. So we did some things here and there, and yeah. So essentially, the numbers that we were interested in were the reduction of the MEMA, because I think the original one of the first things that we observed is even when we tried to see how long it will take for Calcite to plan a large graph, was not that we did not, let's say, had time to wait, but it actually ran out of memory because all those duplicates. Yeah, but getting back to the questions, we did not run the join order benchmark.
Thanks a lot.